while the blue rectangles have, what do you call, small sizes. So what you can guess is still there is error. Obviously they are doing better than white rectangles, but still there is error actually. You can see some parts, where you can, there is either some part where you have some overestimated area or underestimated area, some part left by the blue rectangle. So what should be done next actually? Okay. What should be done next? So what we can do then, we can even increase the number of rectangles actually. I can even, for example, break it down. I can even, break this area into tiny rectangles, and then I will see that, these tiny rectangles are going to fit into this area in a more better way than the big rectangles. Okay. So in other words, for example, if I make this picture again, okay, something like this, and I make really tiny kind of rectangles actually, you can see that, and by the same recipe, what is the method of finding making the tiny rectangles? Split them into really tiny pieces. Split the domain of the function into tiny pieces. Okay, and each such piece, say for example, you choose, say, right end point, okay, and make a rectangle. Right end point and make a rectangle. So you can see that these tiny sticks are going to fit in, are going to fit into the picture, and they give you the areas of area of this unknown picture through through calculating the areas of these tiny pictures actually. Okay, that's what you can do. Now you can ask why I took the right end point always. So what if I took, for example, left end point actually? So let's see what happens. So break this picture into into small pieces and make rectangles actually, and make the rectangle now from the left end points. So in other words, take the left end point, see what is the value of the function at the left end point, and make a rectangle out of it. Okay, make a rectangle out of it. Then what you're gonna do, for example, in the next interval, in the next part segment, take the left end point, and for example, see what is the value of, say, left end point on the curve, and then make a rectangle. Left end point, make a rectangle. Left end point, make a rectangle. Left end point, for example, okay, and make a rectangle. Left end point, its value, make a rectangle. Left end point, its value, make a rectangle. Left end points, its value, make a rectangle of this height. Left end points, its value, and make a rectangle. So now we have, what do you call, these rectangles, okay, but still there is a trouble in these rectangles actually, that are made up from the left end point. So what we should do, so you have these areas which are not covered by these rectangles actually. So what can be done? Okay, what can be done? So let's play, for example, the same game. Okay, let's play the same game actually. We will formalize it later. We will write the mathematics later. The first thing is to really make sense of the idea. Okay. So now take, for example, the left end point of this small interval and make a rectangle. Take the left end point and make a rectangle. Take a left end point, make a rectangle. Take a left end point, make a rectangle, and take a left end point, make a rectangle, take a left hand point, make a rectangle, and let's say take a left hand point, make a rectangle, make a rectangle, left hand point, make a rectangle, make a rectangle. So you can see actually that now the area, as you are increasing what do you call the number of rectangles, okay, as you are increasing the number of rectangles, they are working well actually. Okay, so they are working well, and they are covering kind of more and more area. So this is this big chunk. So if I take this left hand point, you're going to have this. But if I take this end point, you're going to have this actually. So now you can see that if I make the rectangles, number of rectangles increase, and I choose, for example, left hand points, really they are doing better. And I can keep on increasing these number of what do you call rectangles, and I can what do you call create the more and more rectangles, and then count the areas of these rectangles, measure the area of these all rectangles, sum them up. That's going to give you a very good approximation of rectangles actually. The area of under this curve. Okay, this is what that you can do. What could be other strategy? For example, I took left hand point, right hand point. Okay, what should I do next? What if now instead of taking say left hand point and right hand point, I take, for example, let's make first big intervals. Okay, say take a middle point actually. So instead of taking left and right, let's take middle of the each, for example, segment. So take the middle and say make a rectangle of the height which is the height of the middle. So take this middle, see what is the value of the function at this middle, and then make the rectangle of this size. So take middle and make a rectangle of this size. Take middle, so this is the value, make a rectangle of this side, middle, see its value, make a rectangle of middle size, middle, so this is value, make a rectangle of middle size, middle, and make a, for example, a rectangle which has a height which is output of the middle pointer. So again, it's suffering from the same problem that, you know, as you have lessons, so sometimes it's overestimating the area and sometimes it's underestimating the area. So what could be done? The other could be done is that, okay, increase the number of rectangles actually. So increase the number of intervals. And now take the middle of each of these rectangles. So you can choose middle, you can choose right hand point, you can choose left hand point. This increasing the number of rectangles would always work actually. And you can approximate your any picture, okay, your any picture which is made out of or whose top is a curve, okay, whose top is a curve, or the area under this curve, you can approximate it through rectangles. For example, in this, if I take middle and I say compute the area of rectangle, in such a way that the height of it is, I'm bad at picturing, but you can see that what I mean actually. So take this area, for example, take the middle, okay, and see what is the value at the middle, and then make a rectangle out of it. If you increase the number of rectangles, you can see that you can do more and more and more better actually. Okay, you can do more and more and more better. So that's really a very natural trick, okay, that actually I would say anyone would think actually if they have to compute the area. Now, but the good thing about this strategy is that breaking the given picture into more and more rectangles and then computing the area of rectangle and summing them up, this method is consistent. What do you mean by consistent? By consistency, I mean that no matter what picture you make, no matter what curve you take, this strategy would always work actually. This strategy would always work. This strategy would always work actually. Now let's make it a bit more formal. Let's make let's turn this all into mathematics actually. Let's turn these observations into the mathematics. So what is our objective? Again, our objective is to compute the area under the curve by approximating it through rectangles. I mean, you can think of your own theory. You can create your own theory of approximating the area. You can take circles and try to approximate with it. You can take your favorite, for example, triangles and try to approximate the given picture with it. You can create your own theory. There is no harm in it, but you will see that especially in the case when you are talking about areas under a function, this rectangle strategy works very well. So it works very well. It works very well. So let's start with, for example, let's start with, for example, an example. So let's take, for example, a function y equal to x squared, where the x is like the function is defined on an interval 0 to 1. Function is defined on an interval 0 to 1. And let's try to compute the area under this curve in this given interval with this rectangle strategy. With this rectangle strategy. So how does this picture is going to look like? So I'm going really slow so that you can absorb everything. The task is not to just learn mathematics and symbols actually. The task is to really make sense of see that what's going on. So what is parabola? So parabola is this is going to be a parabola like this actually, but we are only interested in, for example, this part of the picture which say starts from 0 and say ends at 1 actually. So this is interval 0. This is the interval 0 to 1. So what we should do? The first thing would be to break this interval into some pieces actually. Some pieces of say for example equal sizes actually. So let's break this interval into some pieces of equal size. So for example, let's break this into say 4 pieces actually. 4 pieces. 1, 2, 3, and you have 4 actually. And imagine that they all are equal size. So if this is if each so if this is a big interval and each one is a sub-interval, so it's a part of that big interval 0 to 1, then what should be the size of it actually? So if I assume that they all 4 are equal, so it is like you have this length and you have broken down into 4 parts. So what should be the size of each part actually? The size of each part should be 1/4. So for example, if this is 0, so this is 1/4. this is 1/4 plus 1/4, so 1/2 or 2/4, and this is going to be 3/4 and 1. So we have kind of 4 intervals. So the first interval, so we kind of broke in this interval 0, 1 into 0, 1/4, 1/4 to 2/4 or 1/2, and then 1/2 to 3/4, and then 3/4 to what do you call that? Okay. And now, say for example, take this strategy, take the left end point on each, say right end point on each part actually. So take for example this input and calculate for example this value. So what would be this value which is corresponding to this? How can I find? So if this curve is y equal to x square, so if x is 1/4, what would be the value that you're going to get at y? Okay, so my function is x square. So the value of the function at 1/4 is going to be f of 1/4, and it's going to be 1/4 square, so it's going to be 1/16. Now make a rectangle that has height what? So this point is 1/16. Okay, so on y-axis. So this means that this height is 1/16. So this is 1/16. So this is a rectangle. This is a rectangle whose height is 1/16, and what is the base of it? You know, the base of this rectangle. So it has size 1/4. So what should be the area? 1/4 multiplied by the 116. Now take, say for example, left end point, this left end point, and compute for example 1/2. So f of 1/2 is going to be 1/2 square, so it's going to be 1/4 actually. So corresponding to this point, you have for example this output. So this height is really 1/4. So this is a rectangle of the size in this interval, which starts from here and 1/4. So this is a rectangle which is which has base. The size of the base is 1/4 and the height is also 1/4. How about the third rectangle? If I want to make f of 3/4, so it's going to be 3/4 square, so it's going to be 9/16 actually. Okay, so now the point that corresponds to it is this. So this is really the value. So f of 3/4 is 9/16, and then I'm going to make a rectangle of this height. I'm going to make a rectangle of this height. And the last interval is really what you call f of 1. F of 1, so f of 1 is really 1 actually. So you're going to get a rectangle whose height is 1. Okay? Whose height is 1. Now you can immediately see a trouble with this, that for example, let's calculate the areas of these rectangles. So what would be the areas of these rectangles? Okay. Say for example, I am calling. So since I have chosen right angle triangle, right end points in each what do you call subintervals. So let me give it a name R actually. So R denotes that okay, I'm talking about the right end points. And how many, for example, intervals do I have? So I have 4. So let me give it a name, say R4. So R4 means that I have splitted my interval into 4 parts, and then I have created the rectangles using the right end point. Okay, using the right end point. So the R4 is going to be what? So it's going to be the area of this rectangle. So what is the area of this rectangle? 1/4 multiplied by 1/6. So 1/4, or you can say that this is equal to, you can also say that this is equal to f of 1/4 multiplied by the length of the interval. And how you can find the length of the interval? 1/4 minus 0. So 1/4 minus 0 plus, so this is height of the rectangle, f of 1/4. So this is 1/4 minus 0. So f of, what are you gonna say? Say f of, next is say f of 1/2. Okay, so I'm talking about this rectangle. So what is the height of this rectangle? So it is f of 1/2. Okay, so this height is what? So if this point is 1/2, this point is f of 1/2 on the curve. So I created a rectangle that has height f of 1/2. So f of 1/2 is the height of the rectangle, and this is the width of the rectangle. So width of the rectangle is really 1/2 minus 1/4. Okay, plus f of say 3/4, and f of 3/4, the area of the rectangle is f of 3/4, and 3/4 minus 1/2 plus f of 1, and the final rectangle is 1 minus 3/4 actually. So what can I do? I can substitute these values and I can get, what do you call, so I have these numbers with me already, so I can substitute them here and I can get, what do you call, area. Now this area is going to be, so when you're going to make all these calculations, so it turns out that this area is going to be 0.46875. 0.46875. Obviously, the actual area, this area, okay, this area is much smaller than these big rectangles actually, the areas of rectangles. So what could be the other strategy? The other strategy could be that, okay, on each subinterval make a rectangle, okay, through the left hand point, left hand point, left hand point, left hand point. So when you're going to make a rectangle through left hand point, so what is the value of the function? So there is going to be no, you know, what do you call, for example, so if I, in this subinterval, if I choose left hand point, so what should be the height of the rectangle? So it's going to be 0, because f of 0 is 0. Okay, for fx equal to x square, f of 0 is 0. So there will be no rectangle in the first interval. In the second interval, if I choose, for example, left hand point, then this is the area of the rectangle. And left hand point, this is the area of rectangle. If I choose the left hand point, this is the area of the rectangle actually. Again, you have a lot of trouble because these are the spaces which are not filled by the blue, what do you call, squares actually, blue rectangles. Okay, so what would be, let's call this, you know, these rectangles as areas as L4. So what should be the recipe for L4? The same as what you did in case of the right hand point. So L4 is going to be f of 0 times 1/4 minus 0. So this is the height of the rectangle times the width of the rectangle. What is the height of the rectangle here? F of 1/4. And what is the width? 1/2 minus 1/4 plus f of say 1/4 times 1/1/2 minus 1/4, and then f of 1/2 times 3/4 minus 1/2 and plus say f of 3/4, okay, times what do you call 1 minus 3/4 actually, 1 minus 3/4. So these are the 4 rectangles whose area is. This has an error, it is overestimating the area, it's giving you the more area than the required area, and this area is going to be a number, okay, which is something in between, what do you call, so this is going to be the less than the required area. So when you're going to compute it, so f of 0 is 0, so this term would be 0. F of 1/4, you already know it. So just substitute the value, compute these areas, and you're going to get what do you call this result, which is going to be 0.21875 actually. So this is the area that you get out of it. Okay. Now, if I call the original area as A, the area of this picture as, you know, what do you call this area as A, then one thing which is sure is that A lies between these two numbers actually. A lies between L4 and R4. L4 and R4 actually. Okay? L4 and R4. This is not good because, you know, I want to reach to the area. So what is the strategy of reaching to this area? The strategy that we have saw basically is that you increase the number of intervals actually. So once you increase the number of intervals, once you create more and more rectangles, you're gonna do better. You're gonna do, what do you call, way better actually. Okay. Let me give you a list actually. Okay. Let me give you a list and then solve this problem in general. So here is an interesting list actually, which says, which talks about say n left end point when you split this into say n parts, and this is what do you call, computing the area of rectangles by splitting this interval into n parts actually. So we know the value when n is 4, okay, so when n is 4 we know that this L4 we computed it to be 0.21875 and Rn is 0.468, what do you call, 75. So when you take, for example, 10 value, in other words, you split this interval into the 10 parts, 10 subintervals, and in each subinterval takes a left end point and create a rectangle and make the sum of those rectangles, okay, then the L10 is going to be a number that is 0.308, okay, 75 for example, and you're going to get this 0.358 and 75. So this is interesting. These two numbers, previously they were, you know, pretty away from each other. This is 0.4, this is 0.2. Now they are, as you are increasing numbers, they are getting closer actually. 3035, so, you know, 0.05 difference. So when you, for example, split this interval into 100 actually, say 100 subintervals and create, what do you call, Ln and Rn, okay. So for 100 this is going to be 0.3234, okay, and this is 0.343, okay, 4 actually. Now if you turn this into, for 100, this is 3 to 8, and this is 338 actually. So they are getting pretty close. How about if I break it down into 1000 actually? So in other words, I make an algorithm of it, and I create, for example, an automated algorithm or a machine or some calculator which can calculate these for me.